I will I will have to point out that although my talk is titled "The Future of PTA Science," I'll spend a little bit of time recapping some of the fun results we managed to get to earlier this year. I will talk a little bit about the physics, the interesting astrophysics, but it's not a deep dive, and I have a very small set of pointers on the things we would like to see in the near future to be able to do good science with PTAs. But there are no answers here, mostly questions, and I'm happy to hear more opinions or suggestions on how to deal with these things. So with that, I'll get started. My name is Golam. I'm a postdoc at the University of Milano Bicocca. I work extensively with the European Pulsar Timing Array, as well as the International Pulsar Timing Array. So you've heard a bunch of talks talking about pulsars, so I won't bore you to death with the details on them, except to say that they're very nice. They're lots of fun. They produce these very amazing pulses, which are like regular clocks, which you can put on the sky, as we did for the EPTA, 25 of them in that central red plot. And you can build a pulsar timing array, which basically hunts for the signatures of perturbations from gravitational waves in the timing residuals, which are the brown dots up there, which we obtain by doing very high precision pulsar timing for 25, or if you want 100 BTAs, 100 millisecond pulsars. And the whole objective of a PTA is to search for what is called the Hellingsdown correlation, which is if you had a bunch of pulsars in the sky separated by different amounts, different angular separations, a gravitational wave, a plane gravitational wave passing over all your MSPs would give you a very specific correlation, which is this colored curve that I put on the left side of the screen. And all that it tells us is that when pulsars are on the same side, the delays correlate to a much higher degree between those pulsars than when pulsars are separated by an angular distance of 90 degrees. While if you switch over to the other side, because the phase between two pulsars separated by 180 degrees, the phase induced by the gravitational wave is not going to be exactly the same. You don't quite recover back to the full correlation that was there originally, but you have almost half the correlation. So this is a weird feature of the Hellingsdown correlation, but it is the specific signature we are looking for in our timing residuals. On the right-hand corner, what I've done is I've plotted a bunch of timing residuals taken from some simulations by Tiburzi, Hobbs et al. In 2016. And the very top one is, again, the Hellingsdown correlation that we are looking for. But there are a number of other possible correlations. Of course, the one which we aren't too worried about is uncorrelated timing noise, which is just fuzziness in your pulsar observations, which will produce a random spread. But there can be weird things like errors in locating the position of the solar system barycenter, which is the EPH panel, which produces a very specific dipolar dipolar curve, but there can also be errors in estimating delays from things like the solar wind or dispersion measure, which then can produce some sort of weird fuzzy patterns. And if I were to add up all of those residuals together, which is what we see in real data, the delays from many different processes are actually mixed in, it gets quite hard to recover back the Hellingsdown correlation with a very high degree of correlation. However, we did manage to do this, and early this year, 29th of June, 4 large PTA collaborations put out some very nice results where we were able to show with a fair degree of confidence that indeed our data sets are now sensitive to the Hellingsdown correlation. So the first plot is from Nanograph, where we can see something of the order of a 4 sigma confidence results, showing that indeed it does look like there is a power law gravitational wave background in our timing residuals. The same thing shows up to some degree in the Parkes pulsar timing array, which is based in Australia. However, the confidence is a lot lower. And you can also see similar results in a very short data set, 3.5 years, from the Chinese PTA, which uses one telescope. And due to the short timing baseline, it's not possible to do exactly the same analysis that we do for the other PTAs. So using some MCMC-based approaches, you can actually estimate a kind of statistical significance, which is a lot higher, which is about 4.5 to 4.6. But the thing to keep in mind is that it's not exactly the same analysis that is being done for the other PTAs that I just flashed. And if you're wondering what did the European pulsar timing array do, that's what we did. So we put together the data for 25 pulsars, and we found pretty much the same results, except we found an interesting phenomenon where our oldest data, when we add in our older data sets, we find a little loss of sensitivity, which we have so far managed to identify as the lack of sensitivity to dispersion measure variations, which leads to some mild mismodeling, which goes away with our fantastic new backends, and then as detection significance increases by a fair amount. So before I move on, I do want to address the elephant in the room, which is that all PTAs appear to be detecting a gravitational wave background, which is much louder than what is expected from most models for supermassive binary black hole formation. And it is quite flatter in terms of the spectral index as well. This is a bit surprising, but it also leads to room for a lot of new physics to be discussed, which has certainly triggered a whole bunch of friends of ours who've been very excited and putting out a lot of results. So the data set that we used for this second data release of EPTA is actually scaled down in the sense that we went from working with the data of 42 pulsars to now we use 25. We have some very good reasons to do this. One is that we don't want to deal with processing every pulsar out there because it just takes too long. It's a data intensive process. It's a astronomer intensive process, and to optimize that, we actually carried out some tests to show us which are the most sensitive pulsars to retain in our array. And using those, we picked the best 25, which recovers about 98% of our total signal. And we've combined data from 5 European telescopes, about a total of anywhere between 12 to 42 different recording systems. So a lot of data to sift through, a lot of analysis to work through, a lot of data checking and verification that needed to be done. But once we had all our data put together, our timing models in place, we are able to do very, very detailed noise analysis. So one of the things we've done with the EPTA, which is quite unique, is that our noise models are very optimized in the sense of we do not use, we do not blindly set a frequency support for the power law models. We optimize the number of frequency bins that are actually supported by the data. This is fairly intensive. We've dug really, really deep into the validity of our noise models, and we've done simulations to check what kind of biases are affecting our results in terms of the timing models, in terms of our estimates of the noise models based on the individual pulsar timing parameters. One of the things I kind of have not mentioned is that although I keep saying EPTA, you will find in the papers that the results are in fact a combination of the EPTA and the Indian PTA. We have actually combined with European data from the Indian PTA as well, and that gives us very high sensitivity, especially in the low frequency regime, and that then enables us to dive into a whole bunch of noise modeling, which specifically deals with dispersion measure variations or scattering variations from the interstellar medium. And this is really the most painful modeling that we need to address. And I've already shown you part of the slide, which is the results up there in the top, showing the Helling-Stone correlation, which we recover with a fair degree of confidence, about 3.6 sigma. But one of the things that you can do, or what we did do, is investigate the astrophysics impact of having such a loud and flat background. And the very first step that we do in our astrophysics searches is to rescale from the standard of PTAs, where everything is quoted at a reference frequency of 1/1 year, to a reference frequency of 1/10 years, because as should be obvious from this plot, the frequency bends at 1/1 year and higher, and in fact pretty close to 1/1 year, are really not constraining, whereas our data are very well constraining as you go towards the low frequencies. What you can then do is you can use this rescaled 1/10 year estimate, which is, I mean, it doesn't change the estimate on the amplitude or the spectral index by a lot, but it does give us something that is a very well constrained 2D posterior. But when we compare that against semi-analytical or models of supermassive binary black hole populations, we find that there is certainly a mild amount of tension. Well, not mild, it's quite an interesting amount of tension that is difficult to explain if you assume that the background, that the gravitational wave background is generated purely by a cosmic population of nearly circularized supermassive binary black hole binaries. There are many ways you can explain these things. One is that there is no reason to believe that the background is generated by a source population which is very, very dense, and which, so in fact, in some of the simulations done by Alberto Susana over the years, we have shown consistently that the background is not a smooth power law. The real background is very unlikely to be a smooth power law. Instead, there are going to be loud sources that which will pop up at different frequencies, and that's kind of what you see on the left-hand plot, that the background is a jagged feature. What we've plotted here are 100 realizations of such backgrounds. And by chance, completely by chance, and without any engineering on our side whatsoever, we happen to have within that selection of 100, one candidate population where we see spikes exactly at the frequency bands as in the data, which are the orange half-violence. But of course, if you, since we're talking about simulations here, what you should do is you should take a bunch of them and average all of them. The average of the simulations, which are the green violence, however, still tends to show a very nice power law fit. But this just highlights the fact that averaging down isn't necessarily going to show you what you recover from the data. We can also try to inject eccentricity to explain the loudness of the background, which is what we tried in on the right-hand side of this plot. Again, in our astrophysics paper, we discuss this in detail. And we find that it is possible to have pure eccentricity, or it is possible to have a population which has a larger number of eccentric binaries. But the probabilities aren't very, very convincing. It is also difficult to produce so many of these sources. On the other hand, what you can also do is to try to generate the same population of supermassive black hole binaries using semi-analytical models based on realistic estimates of populations. So you take your, so you count your sources from starting from simulations like Illustris or others, and you plug in a semi-analytical model to evolve a bunch of supermassive binary black holes, and we find that mostly it's non-trivial to produce such a loud background, but you can inject certain environmental conditions. You can change the rate at which these supermassive black hole binaries grow, and you can get to reasonable explanations of such a loud background. Of course, one of the exciting things would be that if you have such a loud background, there's a good possibility that some of the massive black hole binaries are nearby, and all PTAs have run very deep searches for them. Unfortunately, we don't find them. Wherever we do find candidates, they tend to be dominated by the lines of sight to single pulsars, and then almost always we find that the detection patterns match the antenna sensitivity patterns or the PTA sensitivity patterns in the direction of the given pulsar. So in fact, that gray blob is pretty much one of the lobes of one of the EPTA pulsars hanging out in that direction. So EPTA does not see any single sources yet. That's the sad thing. But of course, as I said, if you have a very loud background and you can't explain it with supermassive antennas, you can plug in a whole bunch of other things which can explain this for you. And that has led to quite an interesting set of results from a lot of people. We looked at it with our internal group of early universe physics people, and we find largely that at this point in time, given our spectral estimates, you can fit anything from strings to curvature perturbation in the early universe, and you can produce backgrounds which are that loud. But I will get to why I personally, and maybe a few others, aren't quite convinced this is entirely possible. But yeah, the evidence for these, so we do some model comparisons in our paper as well. The evidence for these models for the background being purely generated by early universe physics remains weak. It is interesting, however, that you can use the fully EPDA dataset and you can place a constraint on mass if you assume that one of the sources that PTAs are detecting are primordial black holes, then you can place limits on the most massive primordial black holes that we would be sensitive to. And this is paper 6 in the series of EPTA papers, where we do try to investigate some features we see in our in the PTA frequency spectrum. However, again, this is quite hypothetical. There's a lot of modeling that we're doing, and it is not entirely clear that you can produce a background, the background that we think we are starting to see, entirely from even dark matter sources. Since I did promise to talk a little bit about the future at least, the immediate future is that five current PTAs with the PTA nanograph PPTA, the Indian PTA and the Maritime PTA, which is based out of South Africa, we are putting together our data set to produce the IPTA's third data release. For the first time, we have two completely independent data combination pipelines, which make use of Tempo2, which is the standard timing package, and in the new one, we are using a very new package, which is called Point. This is great because we are going to look at 114 pulsars, which in the full combination are able to give us very, very good timing residuals, which is fantastic because that's going to magnify our sensitivity quite a bit. The other good news is that if you have this many pulsars, you get a lot of coverage on the sky, which means that when you try to recover the Hellingsdown correlations, the frequency bins become quite well constrained, or should become quite well constrained. However, this also means that now we have to search through something of the order of 63,000 TOAs, do a lot of timing, debugging, finding bad data, which almost always pops up when you combine data from different telescopes. So the way we have chosen to go ahead with this in the IPTA is to first work with the 20 best pulsars in our data set, which is called the EDR3. We are almost done with the EDR3. We are running our first noise modeling runs. We expect to start seeing investigative results for each of these pulsars soon, although there is no immediate plans to search for backgrounds yet. That timeline goes on till the end of 2025. Once you have such data, such a lot of data, actually, there are things that we have to start worrying about. One is, as with Argos and with any of the new instruments, we're starting to gain a lot of fantastic amounts of radio bandwidth. However, the way precision timing has worked or continues to work, combining all of that bandwidth into a single TOA isn't necessarily increasing our sensitivity. This is because, as most people know, pulsars are fantastic, but they also like to do weird things all by themselves. Sorry, was there something from the room? Okay. You can be careful about choosing what bandwidths you produce your TOAs from. This increases your sensitivity to a whole bunch of things. Mostly the dispersion measure variation modeling becomes much better if you have a large bandwidth and you have a number of TOAs spread in that bandwidth. What is kind of hidden here, and I haven't really shown this, is that fantastic improvement you see on the right-hand side. The blue is real EPTA is a real EPTA data set, which shows an upper limit on the gravitational wave background, and in green is the same set of pulsars, except this time we have reprocessed the data using the optimization which we arrive at on the left, which is to simply choose a better bandwidth to produce your TOAs with. That leads immediately to a constraint. This is significant because if you can do this for 115 pulsars, then immediately your sensitivity to any background signal or any weak signal increases by quite a lot. Um, but as I was trying to get to before, what is hidden in this is that part of the reprocessing actually involved a huge amount of RFI rejection. Um, and when you can do better RFI rejection, your profiles become cleaner and your TOS become better. So somewhere in all this story is, or in the future of all radio astronomy, I presume, is how will we do better RFI rejection? But I won't talk a lot about that, except to say that if we don't do RFI rejection, we will find consistently that the backgrounds we try to measure will tend to become louder and flatter. This is what one of my students looked at in a paper which she will be submitting next week, early next week, hopefully. That if you have bad data in your PTA data sets, it has this very clear effect of, and it has a very clear effect which scales with the percentage of bad data, which is to make your recovered amplitude and spectral index of the background flatter and louder, respectively. This is stuff I've already talked about briefly. We tried this for the EPTA 25 pulsar data set, but there is a step in PTA analysis, which in the Bayesian inference, parameter inference aspect, where we assume that it's fine to marginalize over the timing model parameters. We argue that since the timing model parameters are so well constrained by the frequentist fit, you can just pretend it's a Gaussian and not sample for it when you're modeling the noise parameters of the individual pulsars. However, during the 25 pulsar noise model analysis, we have seen several times that it is not as trivial a picture as that. It does come down to a pulsar by pulsar analysis. Sometimes it is not enough to marginalize over the noise, over the timing model parameters. So of course we want to infer everything using Bayesian analysis. Unfortunately, well, fortunately, the good news is that it doesn't matter what stochastic sampler you use. Results from different kinds of stochastic sampling are more or less compatible, but nested sampling is of course preferable because it gives you a direct, it reports directly the Bayesian evidence for each model that you're testing. But at the same time, all models run, all samplers take forever. So I'm flashing some plots for some analysis we did before we launched the EPTA searches, where we tried to check how feasible it was to use a nested sampler instead of the standard PTM CMC sampler that all PTAs have been using. And we found that depending on the data set, you can have runtimes anywhere between 3 weeks to 6 months. Now, if it was that I had to run this once and I was done with it, that would be fine. But if you want to really do model testing, 6 months on an HPC system is not fast enough. And why do you want to do all of this model testing? Well, that's because if you really want to talk about new physics, or in fact, if you really want to get into the physics, astrophysics of this problem, of the background that you're detecting and what it is showing you, it is very, very unlikely that there is a single source in there. What is more likely is that we are seeing a sum of the background generated by supermassive black holes with other sources. Now, the tricky part is which of these other sources are in there, or which of these other sources are we sensitive to? John Ellis and others have just put out a paper looking at a multimodal analysis, although in this case, they do not, they are assuming that the PTA constraints are perfect. So they just do the multimodal analysis based on the PTA constraints. They're not worried about whether this will change if PTAs reprocess their data. However, if you really want to get into the multimodal physics, you have to do things like this, where you want to make the most sensitive PTA, but you also want to run the same analysis hundreds of times, maybe for all your different models, and then check which is supported by your data using Bayesian model comparison.
Golam,
Yeah.
sorry to interrupt.
Yeah.
I think Aris has a time constraint, so he has to go in about 30 minutes from now. So is it fine to wrap up the talk soon? Okay, thanks.
Yes. So in fact, I think those are my final slides. So the easiest way to make things more sensitive is to get into the new telescopes. SKA, of course, will be fantastic, but there's a whole host of instruments that are coming up before SKA is fully online. I didn't list Maritime here because it's already part of a thing, but we're working to combine data from LOFAR, NANIFAR, and any of the new instruments that come online will make a huge shift forwards in terms of constraining the spectrum. So what I'm showing on the left-hand side is a little guess at the spectra from some of these new instruments. And particularly for individual binary black holes searches, we find a lot of confusion in the high frequency range. There is a very small probability of finding individual sources there. But if you have an instrument like Argos, which is monitoring things on a daily basis, you can, in fact, resolve a lot of the confusion up in the high frequency regime. What you can also do is completely parallel to radio PTAs, go to gamma rays, which is something that is being led in Europe by Aditya at Astron. And the advantage of gamma ray PTAs is that you don't have to worry about a lot of the things that radio waves suffer from. Unfortunately, it also is something that takes time and is a generally unexplored domain. So this needs a fair amount of work. If you have young students or postdocs who are looking for jobs, please get in touch with Aditya. He's just starting off a new group at Astron dedicated to gamma ray PTAs. And I will end on this slide, which is basically, this is really the future. We're going to have a lot of data. It's not going to be possible to manually dig through all of these things to find the minute errors that affect us. We will need workflows, which must be able to be deployed on remote computers and be flexible enough that people can change things quickly. Of course, new instruments may give you better data, but it also gives you a lot more details to dig into in terms of the individual pulsars, in terms of systematics of the telescope. We've already run into the situation where marginalizing over timing model parameters is not going to be enough. So we're going to start looking at more and more Bayesian searches, including timing model parameters. But the most complicated challenge to keep up with things will be the fact that we're starting to have hundreds of thousands of TOAs in our data sets. It's not going to be possible to finish MCMC-based parameter inferences within reasonable amounts of time. So there are two ways to fix this. We can plug in new samplers, and there are a lot of them, but it doesn't look like current implementations are fast enough. You could switch to something called profile domain timing, where instead of many TOAs for a single observation, you fit an entire, you fit a 2D model of the profile simultaneously with other things. Unfortunately, the implementation that is publicly available and any other implementations are simply not fast enough to handle all of the data, neither for pre-SKA instruments or for SKA. And I can stop here.
So Golam, yeah, thank you very much. So